Hello, and welcome to this presentation related to the Poisson distribution. The expression below is the Poisson approximation to a binomial distribution. Note in the expression the symbol e relates to the exponential function we reviewed in a previous presentation, and this symbol is the Greek letter lambda. For your reference, there are previous presentations that contain underpinning knowledge for the contents of this presentation. We previously considered the probability distribution. This was our introductory presentation to probability. We have reviewed the binomial series, shown here. We've considered the binomial distribution, calculating probabilities given various parameters. And there was a brief presentation related to permutations and combinations. As I said, all of these previous presentations provide useful underpinning knowledge for our Poisson distribution presentation. Here's a presentation overview. We commence with an introduction to the Poisson distribution. Poisson distribution is shown here, top of the slide, and how when the value of lambda used within the Poisson distribution is less than 5, it's a very good approximation to the binomial distribution. We then have example 1, which is an application of the Poisson distribution, and we rework example 1, this time using the binomial distribution to show the accuracy between the distributions when lambda is less than 5. That's purely for reference. We then have illustration 1 that uses the Poisson distribution when the n, the sample size or number of trials, is 40,000, and we rework illustration 1 to show why it's preferable not to use the binomial distribution when we have such a large n value. We then consider a further application of the Poisson distribution related to what's termed average rates, for example to failures per week of a particular machine or product, and example 2 is an application of average rates. We consider histograms of probabilities for the Poisson distribution, and that's in example 3. And finally, the presentation concludes with tutorial questions 1 through to 6 for you to attempt at your own pace, although the full solution to question 1 is included within the presentation. And for your reference, here are the approximate start times of the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note all times are rounded to the nearest minute. Let's consider the Poisson distribution. So when the number of trials, i.e. the sample number, usually symbol lowercase n, in a binomial distribution becomes large, and that's usually taken to be larger than 10, the calculations associated with determining the values of the terms in the binomial distribution becomes laborious. For example, to find how many serious car accidents will occur in a town on a given night, if the probability of the serious accident is 0.00001 and the number of cars is 40,000, results in a binomial expression having 40,001 terms. However, for large n values and small probability values p, as in the above example, where the product of n multiplied by p is less than 5, a very good approximation to the binomial distribution is given by the corresponding Poisson distribution, in which the calculations are usually simpler. The Poisson distribution continued. The Poisson approximation to the binomial distribution is defined as follows. The probabilities an event will happen, not at all once, twice, 3 times, n times, in n trials, are given by the successive terms of the expression shown here on the right, e to the negative lambda multiplied by the bracket of 1 plus lambda squared divided by factorial 2 plus lambda cubed divided by factorial 3 plus lambda 4 divided by factorial 4, etc. And these probabilities are considered from left to right. Note that symbol lambda is termed the expectation of an event happening. So lambda is equal to n, the number of trials, multiplied by P, the probability of an event occurring. Let's consider an example. This is example 1. If 3% of gear wheels produced by a company are considered defective, we've got to determine the probabilities that in a sample of 80 gear wheels, A, 2 will be defective, and B, more than 2 will be defective. So extracting the information from the question, the sample number, lowercase n, is 80, is greater than the value of 10, considered large for a binomial distribution, and the probability of a defective gear wheel, symbol P, is 3%, 0.03, which is small. So the product or expectation, lambda, is n multiplied by P, and that calculates to be 2.4, which is less than 5. Hence the Poisson distribution is considered a good approximation to the binomial distribution. So the probabilities of no defect, 1 defect, 2 defective gear wheels are given by the successive terms of the expression shown on the right, called the Poisson distribution. So consider from left to right, expanding the bracket, we have e to the negative lambda plus lambda e to the negative lambda plus lambda squared e to the negative lambda divided by factorial 2 plus lambda cubed e to the negative lambda divided by factorial 3, etc. Example 1 continued. Just repeated this expression for convenience. So the probability of no defective gear wheels, that's the first term in our expansion, that's e to the negative 2.4 in this case, evaluates to 0.0907. The probability of 1 defective gear wheel, that's the second term in our series, lambda e to the negative lambda, that's 2.4 multiplied by e to the negative 2.4, 0.2177. And the probability of 2 defective gear wheels, so that's third term in our series, that's lambda squared multiplied by e to the negative lambda divided by factorial 2, so that's 2.4 squared multiplied by e to the negative 2.4 divided by 2, evaluates to 0.2613. So part A, we have to find the probability of having 2 defective gear wheels in our sample. We can clearly see from the third term evaluated above, that's 0.2613, or 26.1% to 1 decimal place. And part B, the probability of having more than 2 defective gear wheels in our sample. I'm going to calculate that as 1 minus the sum of the probabilities of having 0, 1, 2 defective gear wheels. So 1 minus the first term above, added to the second term above, added to the third term above. So that evaluates to a probability of 0.4303 or 43%. So as a solution to example 1, where we've used the Poisson distribution as an approximation to the binomial distribution. And purely for reference here, I've compared the Poisson distribution results on the previous slide to that of a binomial distribution on this slide. As I said, this is purely for reference. I'm not going to go through any detail with this solution because it relates to our previous presentation related to the binomial distribution. So I'll let you review this at your own pace. The comparison continued here, producing the binomial expansion for this particular problem of sample size of 80. There'll be 81 terms in our series here, and I'll let you review this at your own pace. Comparison continued here. But I'm using the binomial distribution for part A. The probability of 2 defects calculates to be 26.4%. Compare that with 26.1% from our Poisson distribution. Very close correlation here. Comparison continued here. And for part B, using the binomial distribution, the probability of more than 2 gears will fail to meet the specification is 43.2%. And again, we can see that's a very good correlation. With the Poisson distribution, we calculated 43%. So for the parameters given in this particular problem, i.e. large sample size, small probability, and expectation less than 5, we show close correlation between the results from the Poisson distribution compared with the results from the binomial distribution. Illustration 1, the Poisson distribution. So the question required us to find the probabilities of serious car accidents occurring in a town on a given night. If the probability of a serious car accident is 0.00001 and the number of cars in the town is 40,000. So part A having the probability of 2 accidents and part B the probability of having more than 2 accidents. So again, in this case, the n is large, it's 40,000. The probability of a serious accident is small, p is equal to 0.00001. So the expectation, lambda n multiplied by p, evaluates to 0.4, which of course is less than 5. Hence, a Poisson approximation to the binomial distribution may be used. Illustration 1, the Poisson distribution continued. Here are the probabilities of 0, 1, and the probability of 2 serious accidents occurring, shown by the successive terms in the expression for the Poisson distribution. So here's the first term, that's the probability of no accidents occurring, e to the negative lambda is evaluated here. The second term in our expression, probability of 1 accident occurring, is evaluated here. And the third term in our series, probability of 2 accidents occurring, evaluated here. So part A, we have to state the probability of 2 accidents occurring, and that's shown above, approximately 5.4%. It's our third term in our series. And part B, to calculate the probability of having more than 2 accidents, that's 1 minus the sum of the probabilities of having no accidents, 1 accident, 2 accidents. And that evaluates to approximately 0.8%. I've also now considered illustration 1 to show why it's preferable not to use the binomial distribution in this case. Again, I'm going to let you review this at your own pace. It relates to the calculations we performed in a previous presentation related to the binomial distribution. Illustration 1 related to the binomial distribution continued. This slide makes it clear to see that the calculations using the binomial distribution are more complicated than those undertaken using the Poisson distribution. And illustration 1 continued. Here's the final slide related to the binomial distribution. Considering part A of the problem, probability of having 2 accidents from the binomial distribution is 5.4%. That's the same as the value we calculated using the Poisson distribution. And for part B of the problem, the probability of having more than 2 accidents calculates to be 0.8% using the binomial distribution. And we calculated 0.8% from the Poisson distribution. So we can see in this case that the Poisson distribution is a very good approximation to the binomial distribution, and the calculations are simpler. Let's now consider a further application of the Poisson distribution. This is a situation when the probability can be converted into an average rate. So the Poisson distribution can model the probability of observing a given number of events occurring in a fixed interval. The interval might be time, space, etc. related. If the events are Poisson distributed, they occur independently and at a constant average rate. So for example, number of failures per week, number of defects in a length of wire, accidents occurring per month, absenteeism per year, etc. In this type of problem, a Poisson distribution may be defined as follows. The probabilities of an event occurring, not at all, once, twice, thrice, etc. are given by the successive terms in this expression as shown before, taken from left to right. But here the symbol lambda is the value of the average occurrence of the event. Let's consider example 2. A production department has 35 similar 3D printers. The number of breakdowns on each printer averages 0.06 per week. We've got to find the probabilities of having part A, 1 printer breakdown, and part B, less than 3 printers breaking down in any week. So since the average occurrence of breakdowns is known in a defined period, in this case per week, a Poisson distribution can be used. So calculating the expectation of a breakdown for 35 printers, lambda equals to 35 multiplied by the average occurrence, 0.06. If I evaluate to 2.1, that's less than 5, so it's valid to use the Poisson distribution. And the probabilities of the breakdowns occurring, not at all, once, twice, etc., is given by the successive terms in the expression below, taken from left to right. Example 2, continued. So the first term in our expression, e to the negative lambda, that's the probability of no breakdowns, that's evaluated here. Second term relates to the probability of one breakdown, it's evaluated here. And the third term in our expression is the probability of 2 breakdowns occurring, and that's evaluated here. So part A of the problem, you have to determine the probability of 1 breakdown per week. That's stated above, so that's a 0.2572 or 25.7% to 1 decimal place. And part B, the probability of less than 3 breakdowns per week. That's the sum of the probabilities of no breakdowns, 1 breakdown, 2 breakdowns added together, which evaluates to 0.6497 or approximately 65%. Let's now consider the histogram of probabilities. So the terms of a Poisson distribution may be represented pictorially by drawing a histogram as outlined in example 3. Hello, here's example 3. So the probability of a person having an accident in a certain period of time is 0.0003. For a population of 7,500 people, we're asked to draw a histogram showing the probabilities of 0, 1, 2, 3, 4, 5 and 6 people having an accident in this period. So here's the commencement of the solution. So as before, the probabilities of 0, 1, 2 people having an accident are given by the terms in our expression containing e to the negative lambda. So probability of no accidents, probability of 1 accident, probability of 2 accidents, probability of 3 accidents, etc. Note the average occurrence of an event, in this case lambda is the population, 7,500, multiplied by the probability. So the average occurrence is 2.25, that's less than 5, so again we're valid to use our Poisson distribution in this case. Example 3, continued. Here's our full calculations. Probability of no people having an accident, that's the first term in the series. The probability of 1 person having an accident, calculated here. 2 people having an accident, calculated here. 3 people having an accident, calculated here, etc. I'll let you review the other terms at your own pace. Example 3, solution continued. So here is the histogram of the probabilities of people having accidents, given the parameters on the previous slide. So 0 accidents, 1 accident, 2 accidents, 3 accidents, etc. Notice in this case the vertical axis is the probability of having an accident, as essentially the horizontal axis has the same class interval because we're plotting against a number of people. I will now leave you with some tutorial questions to undertake at your own pace. These questions are based on the examples and illustrations shown in the previous part of the presentation. There's question 1 and question 2. Answer stated in the bracket on the right hand side. Tutorial questions continued. Questions 3, question 4, and answers stated on the right hand side for your reference. Tutorial questions continued. Here's question 5, question 6, answers again shown in the square brackets at the bottom of each question. Question 5 can be slightly confusing in its presentation. What was actually required to be found. It's a stock control problem and essentially relates to how many of the tools
should be kept in the stores so that the probability of there being one available when required is greater than 10%. If it helps you in your understanding for question 5, here's actually a plot of the Poisson distribution for this question. Hopefully this provides a hint as to the final answer required.
I will show you the full solution to question 1, but I'll leave you with all the other questions to solve at your own pace. Here's question 1. An automatic machine produces, on average, 10% of its components outside of the tolerance required. In a sample of 10 components from this machine, we've got to determine the probability of having 3 components outside of the tolerance required, and also having less than 4 components outside the tolerance required. And we're assuming here a Poisson distribution can be used. Here's the answer for 3 components outside of tolerance. Here's the answer for less than 4 components outside of tolerance. Notice the first answer is expressed in decimal and the second answer is expressed in percentage terms. I would encourage you to stop the presentation and attempt question 1, but the full work solution for this question is shown on the following slides. Here's question 1, commencement of the solution. I'll let you review this at your own pace. Question 1, solution continued. Again, I'll let you review this at your own pace.
And this slide is purely for reference. It shows a quicker way to calculate the various terms in a Poisson distribution. Here's the original series for the Poisson distribution, showing the first 4 terms. And on the next line, I simply factorise the distribution on e to the negative lambda. What I'm trying to show on the last line is how the various terms in the distribution are related to each other. So the first term in the series is e to the negative lambda. The second term in the series is actually the first term multiplied by lambda. The third term in the series is actually the second term in the series multiplied by lambda divided by 2. The fourth term in the series is the third term multiplied by lambda divided by 3. And the fifth term in the series is the fourth term multiplied by lambda divided by 4. And so it goes on. This essentially relates to the generic formula shown here. It is found that the probability Pn is calculated from the probability of Pn minus 1 multiplied by lambda divided by n minus 1. This shows a quicker way of calculating the terms. I'm now going to revisit question 1 and just show you how this approach could be used to generate the terms in that series.
Question 1 is the solution continued. This slide is purely for reference and it shows us a slightly quicker way of calculating terms in the Poisson distribution that avoids calculating the exponential value every time. So for example, if we consider the third probability, that's for 2 defective components to occur. That would be this probability shown here. We can consider the second probability, that would be for 1 defective component, calculated here, to be multiplied by lambda actually equals to 1 in this particular problem, and divided by the factorial number. The factorial number in this case is 2. So in other words, the third term in the series is the second term multiplied by lambda divided by the number of the factorial. And we can see that evaluates to exactly the same number as shown here. If we now want to find the fourth probability, that's of 3 defective components, so the fourth term in the series relates to 3 defective components. This time we use the third probability, again multiply it by lambda, which equals to 1, and divide by the factorial number, which equals to 3. Here's the 3 in the fourth term. So inserting the values, that's the probability of the third term, multiplied by lambda, divided by the factorial number. Note the factorial number is 3, but the actual factorial has a value of 6. And that evaluates to the same number we calculated previously when we evaluated the exponential. So as I say, that's purely for reference. It's just a way of calculating the third term and onwards in the series in a slightly quicker fashion than always evaluating the exponential. And here's the bibliography used to help generate this presentation. And I hope this presentation has been of use to you. And as always, thank you for viewing.